So today we will introduce the concept of probability. Okay. So probability. But to define probability, we need to define events, because probability is always the probability of some events. Okay, but what are events? Events are like the face of a coin, or it can be accidents, or it can be the number of a die, or it can be anything. But we cannot develop different probability theory for different events, right? So we need to abstract all those events into some mathematical structure. Uh, and that is called sample space. Okay. Okay. So this is the first concept for defining probability. Sample space is nothing but a set. It's a set, that's all. And let's say omega is a sample space. So that means this is just a set. Then elements of omega are called outcomes. So elements of omega are called outcomes. So in essence, we consider one set that contains everything we want to consider for a particular problem, which means it contains all the possible outcomes of some phenomenon. Then we define event as a subset of omega. A subset of a sample space is called an event. So since there can be many kinds of subsets for a particular set, sample space, so there are corresponding events. Okay. So after all, the sample space is a set and an event is a set. So everything reduces to the language of sets, set theory. Okay. So one example. Let's say omega is heads and tails. So we are considering flipping a coin. The results are heads or tails. So there are only two possible outcomes. Okay, so we are throwing a coin. Maybe it's 50 cents. So heads or tail. So this is a possible sample space. When we are considering coin flipping problem, then there are only two possible outcomes. So this is a good enough sample space for us. So this head is one outcome, and this tails is another outcome. And possible events. Remember, one event is one subset of omega. Okay, so there are, for this sample space, there are four possible events, subsets. So one is empty set, or another is omega itself, which is same as omega. Another one is the set of heads only, one element. Another is a subset, yes, T contains one element again. So these are possible events in this case. Easy. So, but when we consider probability, not every event can be assigned a probability value. Well, in this case, it's okay, but if this sample space becomes, for example, uncountable, then it becomes very difficult to define probability very consistently. So we need some rules which must be satisfied by events. Okay. So in order to define those events, we define algebra, concept of algebra. It's an algebra of subsets. Okay. So maybe this is a very unfamiliar concept, so be careful. And let omega be a sample space. And F be a collection of subsets of omega. So in other words, you can say this F is a collection of events. Okay. Then this F is called an algebra if this satisfies the following three conditions. 1. Omega itself is an element of F. Okay. 2. If A is an element of F, then A complement is also an element of F. And 3. If A and B are both elements of F, then their union is also an element of F. Excuse me. So, this F is a collection of events. It can contain all possible subsets of omega, or it is possible that this F contains only some of subsets of omega. But in any case, if this F satisfies these conditions, then this F is called an algebra. Okay. But why do we do this? Because later we want to define probability, but we do not define probability values for any subsets of omega. Only for a limited collection of subsets of omega, right? And those limited collection is characterized by these conditions, these three conditions. Okay, so we define probability only for the collection of subsets of omega that satisfy these conditions. These are actually required if we want to construct a consistent theory of probability, as we will see later. Okay. This may sound too abstract, but you will get used to it. Okay, so here's one example. Again, consider coin tossing problem. So our sample space is head and tail. Let's say F is a collection of all subsets of omega. So that is empty set, H, T, and omega itself. Now, so this F is a set of sets. It's a set of sets. Sets. Okay. Now let's check if this F satisfies the three conditions of algebra. Okay. As we can see, this omega is a member of F. So it satisfies the first condition. Two was if any element of F, if A is any element of F, then its complement should be also an element of F. Okay, so that means if we take empty set, then its complement is omega, right? Which is an element of F. So empty set is an element of F, and its complement is omega, and it is an element of F. So this is okay for this. Now take this subset. This is an element of F, H. It's a subset consisting of only H, and the complement of this subset is the subset consisting of T. This is indeed a member of F. So this is okay for this. Now take this subset consisting of only T, and its complement is the subset consisting of only H, which is an element of F. So this is okay too. What about this? H and T. This is actually omega itself, right? So the complement of omega is empty set, which is a member of this F. So all the elements, if we take any of these, its complement is also a member of this F. So the axiom 2 is satisfied. Then let's check